Hi, this presentation is for EMS 472 on variables. And prior to watching this presentation and listening, you should have read Developing Meaning for Algebraic Symbolism by Lannon and colleagues and completed the PTMT Chapter 3 materials. So what I'm going to talk about is some research done by Stacey and McGregor. They are two Australian math educators that studied students' ideas about symbolism that they bring to algebra. And their work was published in an article in 1997 that I'm going to be referencing throughout this presentation. So Stacey and McGregor interviewed over 2,000 students ranging in ages and also experiences with algebra to try and understand what kinds of understandings they had about symbols. And so they found four major misconceptions. The first is that students' interpretations of algebraic symbolisms are based on other experiences that are not helpful. So a lot of things that they do in elementary school and the ways that they see symbols out in the world are really not helpful for the way that symbols are used in algebra. Secondly, the use of letters in algebra is not the same as their use in other contexts. So, for example, games or things like secret codes that each letter corresponds with a specific number that can be used to reveal hidden messages. Students have these sorts of things presented to them in elementary school, and so when they get to algebra, the way that we're using letters is very different than those sorts of contexts. And even in math, the way that we use letters can be different. So, for example, we use things like cm to stand for centimeters, or in for inches. So we use those as a way to describe units, but it's different than the ways that we use letters in algebra. Third, the grammatical rules of algebra are not the same as ordinary language rules. So, for example, when we say 10 more than a number, the way that we write that in algebra is very different than the way that we say it or read it. Another example, 3 less than 2 times a number. The way that we say that using the English language is very different than the way that we write it with algebra. So in a lot of ways, algebra is a language in and of itself. And fourth, algebra cannot say a lot of the things that students want it to say. So students have these ideas about what they see, but then don't know how to express that using the language of algebra, which can be really frustrating for students. So, as I mentioned, the authors interviewed over 2,000 students, and what they did was they asked them this question. David is 10 centimeters taller than Khan. Khan is h centimeters tall. What can you write for David's height? So take a second to think about that. And of course, we have a lot of experience with algebraic symbols, so we might write something like this. David's height equals h plus 10. And we understand that h is representing a value for Khan's height, and we would add 10 to that to describe David's height. So when they presented this question to students, they summarized their responses in this table. So I would suggest that you pause and take a few minutes to read through the responses and try and make sense of them. Okay, hopefully you had a chance to read through the responses and try and make sense. We'll talk about a couple of them. So, some interesting things. For example, the first response, DH, this abbreviation stands for the word David's height. Makes total sense to a student, but for us, mathematically, is not accurate. Similarly, the second response, C plus 10 equals D. So this is probably the closest of all these responses to what we would describe as correct. But the students in this case are completely leaving H out of the equation and disregarding that aspect of the problem. But in their mind, it makes sense that C would stand for Khan's height and D would stand for David's height. The third response is kind of the opposite of that, where the students rely heavily on H and assume that H can denote any height because it represents that concept. The next two responses are similar to that secret code idea that I talked about earlier. So a student would respond to 18 since H is the 8th letter of the alphabet. 8 plus 10 equals 18. Makes total sense. Same thing with the next response. The 10th letter after H is R. So David's height must be R. Take a look at the second to last response, H10 or 10H. A letter next to a numeral indicates addition. So this is really interesting, and it can connect to something like Roman numerals, right, where we use addition and subtraction with letters to represent numbers. So for example, 6 in Roman numerals we would write as VI. And that VI, we would actually add 5 and 1 to get 6 as our equivalents. So the interesting thing to note about some of these is that even though they're completely, the answer itself is wrong, it can reveal that students actually do have an understanding of the situation. So for example, 18, the response of 18, here students understand that I'm adding 10 to get David's height. So even though that's a completely incorrect answer, it does reveal that the students do have some understanding about the situation. So the article concludes with some suggestions for teachers. First of all, it's important to use algebraic notation often, but be sure to make connections to the symbols, context, or other visual images. We're going to talk a lot about this in our next couple classes. Secondly, emphasize that variables stand for numbers, not for names of things. So for example, instead of saying use C to stand for cost, we could say something like use C to stand for the number of dollars. So really emphasizing the fact that that variable, that letter, represents a number instead of a thing. When working on number patterns and functions, ask students to explain the relationships they see in words, then transition to algebraic expressions and equations. And again, we're going to talk about this a lot in our next couple classes. And finally, appreciate that your students come to algebra with rich prior experiences of symbols. Just recognizing that your students have different experiences than what we want them to be able to do in algebra is important, and then using those experiences to build our instruction.